Hello student, nice to have you in this lesson. In this lesson, we shall be considering oscillation. And the question to us is, what is oscillation? What does oscillation mean? What can we actually say about oscillation? Actually, oscillation is the to and fro or forward and backward motion of a body between two limits as a result of energy supplied to the oscillating system. There are some key points that you need to take note when defining the word oscillation in terms of physics. One is the fact that it's a to and fro or forward and backward motion, meaning that as far as oscillation is concerned, it's not a straightforward or a straight line or transitional kind of motion. It's a motion that involves a forward movement or a kind of backward movement. Then the movement is between two limits. That's another key point you need to take note. It's between two boundaries, two limits. That is where the motion seems to exist. Then also, the motion cannot occur without the application of energy. That is the third point you need to take note when defining the word oscillation. Energy is required for a motion to occur. Of course, we know that for a body to be set of motion, there must be an application of energy. It is the energy that causes the transition. It is the energy that causes the movement. Okay, so the energy supply will determine the two limits, the length between the two limits or the two boundaries. So please, let's take note of that. Now let's consider some examples of oscillation. Actually, we have numerous examples of oscillation. I will just mention a few of them. The first one is a test tube bobbing up and down in water. In this case, we're actually talking of a loaded test tube. A loaded test tube. A loaded test tube bobbing up and down in water. Such a movement is actually an oscillatory movement. Then another one is a simple pendulum. A simple pendulum. Wow, you must have seen a simple pendulum set up in the laboratory before. All what you just need is a pendulum bob, then attached to a string. Then you set it on a particular displacement, and when you release it, you see the pendulum bob oscillating from one point to another. That's another good example of oscillatory motion. Then another one is a vibrating spring with an attached mass. A vibrating spring with an attached mass. Okay, all you just need to do is to attach a spring to a particular mass. Okay, especially an elastic kind of spring. Now when you display the mass attached to the spring at a particular distance and you release, what you're going to notice is that the spring begins to vibrate, meaning that it exhibits a vibratory motion, or what I call an oscillatory motion. So what you are going to notice is the mass will be moving. It depends on the direction you set the mass. If it's a vertical direction, then you see the mass, the spring moving up with the mass attached, moving up and down. And if it is an horizontal displacement, then you're going to see the mass moving left and right, okay, as the spring vibrates. Okay, from here, let's consider some terminologies in oscillation. Terminologies in oscillation. Some of these terminologies I'll be mentioning are so expedient because those are some of the things we are going to be making do of. We're going to be using them as time goes on in the lesson, in the course of the lesson. So you need to know every bit of each terms. Okay, I will be mentioning, okay, right from here. Okay, let's see the first one. We have equilibrium position. equilibrium position. In oscillation, we have a particular position we refer to as equilibrium position, and that equilibrium position is actually a fixed position of an object when not oscillating. When an object is not oscillating, meaning that there is no movement at all, okay, the position of the object, or what we call the oscillating body, that such a position is the equilibrium position. Why do we call it equilibrium? Because at that point the position of the object is fixed, is at rest, so it's not moving. Okay, so we can as well say that at that same point the object exhibit a zero position. Okay, meaning that there is no displacement. We can't actually determine the distance or the displacement of the object at that very point. Okay, meaning that it's not moving. Another one is displacement. The second terminology there is displacement. Displacement is actually the distance from equilibrium or fixed position. Okay, what do I mean by that? What I simply mean is, if I displace the oscillating object from its equilibrium position, meaning that the point where it wasn't moving at all, I displace it, okay, away from that point. The distance covered between its initial position and its current position is what we call the displacement. Okay, the distance covered between its initial position when it was not moving to the position, its current position after being displaced, is called the displacement. Okay, let's see another one. We have amplitude. Amplitude actually will represent amplitude, or we at times represent with x maximum. In some textbook they can use any other symbol, so don't get confused. So amplitude is actually the maximum displacement of an oscillator, or you can simply say oscillating body from the rest position. Rest position is same as the fixed position or the equilibrium position. So the maximum displacement, that is the highest displacement we can ever have after displacing an oscillating object, is actually called the amplitude, and that is in respect to the rest position of that object. Let's see another one. We have the frequency, usually be represented with small letter f. The frequency is actually the number of complete oscillation per unit time. What do I mean by that? Meaning, what I simply mean is that if I have numbers, okay, it depends on the number of oscillation, okay, the number of oscillation cover within a given time is my frequency. So meaning I can have about 2 oscillation in 1 second. I can have about 5 oscillation within a second. So it depends on the number of oscillation. So the number of oscillation per unit time or per unit second is simply the frequency. Okay, so that means from what I've said here, mathematically we can actually say the frequency f equals n over t, where my n there is actually the number of oscillation, and my capital T there is the period, meaning the time it takes to cover the number of oscillation. Now if we take the number of oscillation to be 1, that is when n equals 1, that means I'm saying when I'm having just 1 oscillation, then obviously what I'll be having will now become f equals 1 over t, meaning that I'm having 1 oscillation, okay, in 1 seconds or per 1 seconds. You understand that the time, the unit of time rather, is actually in seconds. Okay, so going by what I have now, I can as well derive the unit for frequency directly from the formula. So if my time is actually seconds, so I can as well simply say that the unit of frequency is per second. That is 1 over seconds per second. Or I can say in hertz. Okay, in hertz. That's another unit for frequency. Let's see another terminology. The number 5 here, we have period, which is usually be denoted with capital letter T. The period is the time taken to complete one oscillation or cycle. One oscillation or cycle. The time it takes just to complete one oscillation is my period. Don't forget this. It's very important because we are going to be reminding ourselves about this as we go on in the course of the lesson. Okay, so the time taken to cover just one oscillation is my period. So from this definition, I can actually derive a formula from there directly by simply saying T, which is my period, equals 1 over frequency. That is, my 1 there is actually standing for that is 1 oscillator per unit oscillation rather. So that 1 actually is standing from what I already got from the formula I have initially obtained in the fourth terminology I gave to you, which is the frequency. You know what I gave to you right there was F equals 1 over T. Okay, so if I make T the subject of the formula, all what I'm going to get at the end of the day is going to be 1 over F. And don't forget, my 1 there is standing as 1 oscillation. That is when n equals 1. So do not forget this. Let's see another one is angular frequency. Angular frequency is usually be denoted with a symbol called omega. Okay, so that's what you can see right there. Omega looks like W. Okay, so whenever you see such symbol, it stands for angular frequency. Now, this is the frequency of an oscillation, of an oscillatory motion expressed in radians per seconds. In radians per second. So the frequency of an oscillatory motion, which is expressed in radians per second, is actually my angular frequency. Now I need to say one thing here. This angular frequency also have similar attribute or similar characteristics, or rather I can say it have similarity with what you already know from circular motion as per angular velocity. Okay, so it has similarity with angular velocity. Okay, so if you put what you already know from circular motion as per angular velocity, you could remember that angular velocity is actually omega rather. Omega equals V over R. Omega equals V over R. And we can as well say omega equals 2 pi over capital T. Omega equals 2 pi over capital. That is from what you already know from circular motion. So the same thing is applicable here. Okay, so we are not deviating from that. It's still same approach to this. So mathematically speaking, I can say omega equals 2 pi over T. Omega equals 2 pi over T. But don't forget that I can actually break this down to as well say omega equals 2 pi over 2 pi times 1 over T. And 1 over T is already frequency from the fourth terminology I gave to you. Okay, so if I substitute directly for 1 over T in this equation number 3, all I will get from this equation number 3 is this. Omega equals 2 pi F. Omega equals 2 pi F. All what I've simply done is to substitute for 1 over T. Okay, and if I substitute for 1 over T, I'll be putting in my F, so I end up getting omega equals 2 pi F, which is my fourth equation right there. Okay, from here we move straight away to types of oscillation. Types of oscillation. We want to see different kinds of oscillation we have. So let's consider the first one. There are three. We have three of them, and the first one there is free oscillation. We have the free oscillation, and the second one is forced oscillation, and the third one is damped oscillation. Free, forced, and damped. I call it FFD. Okay, so you can give it your own tag. Okay, whatever you know you can use to remember these three type of oscillation, go ahead and use such so that you can recall the three, okay, at a go. So let's start with the first one there. We are starting with free oscillation. Free oscillation. Okay, so what's free oscillation all about? Before I begin to dissect what free oscillation is all about, let's just look at the literal meaning of what we are trying to consider here. If we talk of free, we say something is free. Well, that means that thing is at liberty. That means there is no restriction. That means there's nothing that's limiting it, or there's nothing that's actually influencing it. That means it's a freedom. It have the liberty to do whatever. So that is just free. Literal meaning of being free. Okay, now when we talk of oscillation, I've explained oscillation before. So let's combine the meaning I've given to free oscillation now. So if we combine what we already know about oscillation, knowing full well that oscillation is a to and fro or forward or backward movement between two limits as a result of energy supplied, then we want to see how we can link that up, okay, in terms of the oscillatory body being free. So in this case, we'll be talking of something like this, that free oscillation is actually a simple harmonic motion with a constant amplitude, period, energy, when no external force is applied to sustain it, meaning that there is nothing that is actually influencing it, there is nothing that is actually restricting it, and that thing, okay, could be an external force. Maybe it could be a pressure, it could be humidity, it could be temperature, it could be anything. Okay, so no external factor, no external force is affecting the movement of the oscillation, meaning that the oscillatory body is at liberty, it's moving within a constant amplitude, period, and energy. So it's maintaining same energy applied, same period covered, then same amplitude, and that is why it is regarded as simple harmonic motion. Okay, so all this is some of the things you need to take note, especially all these words that are written in bold letters. They are actually the key points in the definition. So when you are asked to define or probably you are asked the meaning of free oscillation, these are the key points that must reflect. Number one, it's a simple harmonic motion. Number two, it has a constant amplitude, period, and energy. And the last one is that it's not being influenced, so there is no external force, okay, that is applied to sustain it or to influence it. Okay, so these are the facts that you need to know about free oscillation. Okay, another thing you need to know is the fact that free oscillation does not occur, practically speaking. What do I mean? I mean, practically speaking, it is not obtainable. The free oscillation is not obtainable. Why? Because there will always be some amount of resistive force. There is no way, even in the laboratory, if you try to set up a simple pendulum and you set it on motion and it's moving, gradually you will see some amount of resistive force acting on the pendulum ball, either from the environment as a result of air resistance, or probably due to some other factors. So practically speaking, we cannot have a free oscillation. Okay, but we can come up with the fact that, oh, if all other factors, all other environmental factor or forces is maintained, then definitely we can actually have a free oscillation. Okay, now let's see an example of free oscillation. An example is a simple pendulum, just as the one I've mentioned earlier on, or a vibrating spring with a mass attached in the absence of external force. Please take note of this word. It's very, very vital. In the absence of external force. Okay, that is the key point there. If you mention a simple pendulum or a vibrating spring with mass attached, and you don't put this key point, then you've not actually mentioned any example, because a simple pendulum can actually be another kind of oscillation if this key point is not reflected. So that key point must reflect in the absence of external force. It's very, very important. Now let's see simple harmonic motion. When I was defining the word free oscillation, I said is actually a simple harmonic motion. So the question now is, what is really a simple harmonic motion? Okay, so let's take a look at that. Simple harmonic motion, also known as S.H.M, is actually the motion of a body. Okay, and not just any kind of motion, but rather the body move about a fixed or equilibrium position, such that its acceleration is proportional to its displacement. From that point, I'm referring to the equilibrium point now. From that point, and it's always directed to that fixed point. It's always directed towards or to the fixed point, or opposite to the direction of the displacement. What do I mean by this? Let's analyze this definition. Okay, first of all, I said S.H.M, which is simple harmonic motion, is the motion of a body about, see the word there, about a fixed or equilibrium point, meaning that the object is actually moving about its fixed position, that is its rest position before it was displaced. So it's moving about that point. Okay, and it's doing that in such a way that the acceleration, which I represent with the letter A, is proportional to its displacement x. Okay, so its displacement, I've told you, I've explained that earlier on, is the distance between its rest position, okay, to its displaced position, that is the position it is after being displaced. Then you already know what acceleration means. You know where there's a change in velocity of the object. So as the object moves from one point to another, there's always a change in velocity. So when the acceleration of the object is directly proportional to the displacement, not just only being directly proportional to the displacement, but also from that point, and it is directed, or it is a way, okay, it is a way, or it is rather directed towards the fixed point, then I can say it's a simple harmonic motion. Okay, if it is directed towards the fixed point, I'm still referring to the equilibrium position. Okay, or you can say it in another way, that if it is opposite to the direction of the displacement. What do I mean here? That is when the acceleration is opposite to the direction of the displacement, or in a way, when the acceleration, okay, is away or is always directed towards the fixed point. Okay, that's another way to say that. Let me use a diagram to explain this better for you to be able to understand. Here I have two different diagrams. The first one here is a simple pendulum. This is a simple pendulum setup, and this is actually a spring attached to a fixed mass. Okay, so whatever I explain here also goes in a way to this, is applicable to this. But let me start up with this. Now, this straight line, this vertical straight line, is indicating a string attached to a pendulum bob. This is a pendulum bob. Now, at this point, the pendulum bob is at a fixed point, meaning that it's not moving. Okay, now by the time I display the pendulum bob towards this direction, if I display this pendulum bob at position B, I display it towards position C in the right direction. Okay, what I've simply achieved is an angle. There's an angle in between them I've been able to achieve, and that angle I've been able to achieve between them is what we call the angular displacement. This is an angle right there that is between its equilibrium position and its current position after being displaced. Okay, so that angle I label it that is theta, angle theta, and that is angle in radian. Now this angle theta is also equivalent to omega t. Okay, omega is actually my angular frequency, and the t there is the time. And I must tell you that this omega t is approximately equal to sine theta. Okay, where theta there is very, very small. Okay, is equivalent to sine theta, where theta is very, very small. Now, coming back to this, after displacing the object to this point C, and I mean at this very point C, this is taken as the highest displacement or the maximum displacement. Okay, because that is just the highest fixed point, I mean the highest limiting point I can ever obtain right there. That means if I actually go ahead and pull this pendulum bob again farther from this point C, if I pull it away again, definitely this one will no longer become my maximum displacement any longer. So where the new position I have now becomes my maximum position. But as far as this is concerned, this is my maximum position for now, because that is the highest limiting point I have. Okay, so at this point I have my maximum displacement. Now if I release the object at this point C, obviously the object will not go in this direction again. What will happen is the object will return and follow this direction, passing through this fixed point, then coming to point B. Okay, so and that is referred to as toe movement. Now when the object gets to point A, when the object gets to point A, what we are going to notice is the fact that the object will also take a move from point A back to point C, following this equilibrium position. Okay, so in other words, that same movement from point A to point C is regarded as the through movement. So in other words, I have a toe to point B, then through to point C, and that makes it an oscillatory motion. Now back again to this, what I want to explain now is how does the maximum displacement relate with the acceleration, because from the definition of the simple harmonic motion, I said acceleration is directly proportional to the displacement. So in other words, here I have the displacement. When I release it, it goes in this direction. Now moving in this direction is actually a negative direction, because honestly from our graph, when you are moving horizontally leftward, just as I have it, if I'm moving in this direction, that is negative. If I'm moving in this direction, that is positive. So if the pendulum bob is moving in the negative direction, then the acceleration is negative. If the pendulum bob is moving in the positive direction, then it is a positive acceleration. Okay, so in other words, this object is moving towards the fixed point. That is what I said right here. always directly towards the fixed point. So the object will move towards the fixed point, okay, along the fixed point and towards it. So doing that, meaning that it is actually opposite. So, or another way is that it is opposite to the direction of the displacement. That is, when the object moves this way, it is opposite the direction of the displacement. The direction of the displacement is like this, which is rightward, and the direction of the object is like this, which is completely opposite to each other. Okay, so in that case, that means acceleration is opposite the maximum displacement. So with this, we'll be able to affirm and confirm the fact that they are opposite in direction. Even if we consider point A, when the object gets here, gets to the limiting point here, of course it's going to return towards the fixed point, and it's going to move in this direction, which is positive. That's why acceleration is positive here. Okay, but the maximum displacement in this particular direction is negative, so meaning they are still opposite in direction. So either in whatever direction, there will still be this exhibition of opposite direction between the acceleration and the maximum displacement. Now the same thing goes to this vibrating spring. Okay, this is the equilibrium position when the object is not moving, and so if I displace this object downward, what I'm going to have is, at this point I will have my maximum displacement. And you know, from your graph, when you are going downward, you are actually tending towards the negative, and when you are going upward, you are tending towards the positive. So at this point downward, I have my maximum displacement but negative. Now when I release this object at this particular point, the object will bob up. It will bob up, and when it goes up, of course it's moving in the positive direction. Okay, and so because it's moving in the positive direction, acceleration is taken as positive because it's going upward. Now on getting to this point, which is another limiting position, okay, where I have another maximum displacement which is positive, now the object returns following through the equilibrium position again, and it continues like that. It keeps exhibiting. Now when it's returning, because it's moving downward, acceleration becomes negative, meaning that acceleration in this case is opposite the displacement. The same thing to this point is positive to is positive, while the displacement is negative, meaning that they are as well opposite to each other. Okay, so from what I've said thus far, I can come up with a mathematical expression from the definition. I can say that A, which is my acceleration, is directly proportional to negative max x maximum, that is maximum displacement, which is what I have right here. Positive A is opposite to negative maximum displacement. Okay, and I've told you that they are directly proportional, so that's why I have this. Or I can as well say negative acceleration is directly proportional to positive maximum displacement, which is what I have in this region, or in this region. Okay, so with this now, if I remove the proportionality sign, I will end up getting a constant, and this is what I will end up getting. I will be having A equals minus omega square x maximum minus omega square x maximum. Okay, now the question is, how do we end up getting this negative? Of course, that is just as easy as simple. From what I have here, if I remove the proportionality sign, of course I have my constant coming, and there's already a negative here, so that's why I have negative omega square. Or if I even use this, I will definitely be having negative A, which is acceleration, equals omega square x mass, and if I multiply both sides by negative, I will end up still getting this equation number 5. Okay, now let's see some other things about this equation we've just derived. From this equation, I've said it that omega squared there is a constant, And we can obtain this constant, which is omega squared, by finding the gradient of the graph of A against X. Okay, if I plot the graph of acceleration against displacement, the gradient of such a graph will give me omega square. It's as simple as that. So we're going to see how we're going to go about that, but there's some other things you need to understand about this same equation number 5 we've derived. Now this equation number 5 is as well regarded or referred to as defining equation for S.H.M. Defining equation for simple harmonic motion. Another thing again is that the acceleration A, which is this, varies from time to time. That is, it's not constant. Okay, the acceleration in this case is not constant. Please take note of this. Acceleration in this case is not constant. It can only be constant if it is a free oscillation. If it is a free oscillation, the acceleration can be taken to be constant. Okay, but if it is not a free oscillation, in every other kind of simple harmonic motion, acceleration is not constant as far as simple harmonic motion is concerned. Okay, now let's see how we can actually obtain the defining equation for S.H.M, which is that equation number 5 we've obtained. So let's say how we can graphically represent that. I said we can obtain that, the constant by using a graph, which is acceleration against displacement. So let's see how we can go by that. Okay, right here I have the graph of acceleration against displacement x. Okay, and on the vertical axis I'm having my acceleration, on the horizontal axis I'm having my displacement. Okay, and this ax, what it stands for, that is maximum acceleration, this maximum displacement in the negative, this maximum displacement in the positive, and this maximum acceleration in the negative. Okay, so what we want to do now is we want to see how we can obtain the constant omega square. Okay, so I told you to get that, all we just need to do is to find the gradient of the graph. Okay, so if I'm to determine the gradient of the graph right there, it's very easy to get. All I just need to do is to plot the graph. But meanwhile, the question is, how do we even end up getting this kind of graph? How do we end up getting this kind of graph? It's very simple. Now let's start with the displacement. At when the displacement is maximum, okay, what you need to know is that acceleration is maximum. Acceleration is maximum at maximum displacement. Take note of that. If you need to put this down, it's very important. Now acceleration is maximum. Now I'll just need to plot my graph. When x is maximum, acceleration is maximum. So that means at this point I will trace it this way, trace it this way, trace it this way, then I'll make my asterisk here, then trace it down. Okay, because acceleration is maximum at maximum displacement. Now when the displacement is a 0, acceleration is 0, meaning that my plotting point will be at this point, because at this point I'm having 0 displacement and I'm having a 0 acceleration. Now when the displacement is maximum again in the negative direction, acceleration is again maximum. From what I've showed you guys in the diagram, okay, so acceleration is maximum. Okay, so all I just need to do is to plot the graph. I'll just trace it from here at maximum acceleration, then I trace it down. So I have this asterisk. So I can keep doing that. Then I can as well go from here. Then have an asterisk, then trace it up. So meaning that at this point, at maximum displacement, this negative acceleration maximum, so it should be in this direction, not in this direction. Please take note of that. It ought to be in this direction, not in this direction, because I've said it that they must be in opposite direction. They must not have same sign. So if one is negative, the other should be positive. So it will be in this direction. So you asterisk it here, then you bring it down. So that is how to have it. So all what you just need to do is to connect the plotting point. So you can have it this way: connect this to this, then to this, or the one you have here, connect it to this, then to the one you have here. So you will still end up getting a same graph. Now I've only used 2 points here, so I use this, and I use this. Okay, now if I'm to find the gradient, then I will have to consider either this part, or I consider this part, or I consider this part. Whichever part you want to consider, you end up getting the same answer. Now if I'm considering this part, this is my vertical, which means change in acceleration, and this part is change in displacement. Okay, so if I'm to do that, my gradient from here will obviously be this. So that will be negative change in acceleration over change in displacement. How do I get this? I've said it. That's change in this over change in this. But you have to be very careful, because displacement here is negative, so that's why it's bearing negative. If I'm using this side is change in acceleration, and this side is change in displacement. Okay, and don't forget, acceleration in this side is negative, so that's why it's bearing a negative sign here. So that's change in acceleration over change in x. Now how do we now end up getting that equation? Now by using equation of a linear graph, because this is a linear graph, and the equation of a linear graph is actually y equals mx plus c, where y is our vertical axis, x is our horizontal axis, m is standing for gradient, and c is standing for an intercept, okay, or a constant. Now from what I have here from this equation, I can have a relationship. Already I've gotten my m, which is a gradient, to be negative change in a over change in x, which is delta a over delta x. So if I come here and substitute, what I'll end up getting is this. Okay, so my y, which is a, which is standing for acceleration, negative axis, vertical axis rather, that I've substituted for m. I have this. The x still remain my x, which is for displacement. Then my intercept, that is 0. There is no intercept, so it's passing through is 0. So I have a 0. Now from what I have here, if you can remember from the idea of circular motion, there is a formula that goes like this: omega square equals delta a, which is change in acceleration, over delta r, which is change in radius. Okay, so it's similar to what we have here. Okay, the change in radius there is also indicating change in displacement. Okay, so if I relate that together, I will end up with this. So I'll be having a equals negative. Now I have substituted for delta a over delta x, which is omega squared, and what I have here is x. Already this is 0, so this is the defining equation we'll be able to derive by using the graph. Now this graph confirms the defining equation for S.H.M. Now from here, let's consider the solution to equation for S.H.M. Solution to equation for S.H.M. Okay, we've gotten an equation for simple harmonic motion. Now we need to find the solution to the equation. Now there are certain things you need to know, that as far as the solution to equation for S.H.M is concerned, we can actually determine it either graphically or mathematically. Okay, so there are two ways to it. Either we graphically find a solution, or we mathematically find a solution. Now we're going to consider firstly the graphical aspect of finding the solution to the equation for S.H.M. But there are key points we need to know when using the graphical method. Okay, so key points you need to know. Number one, the number of oscillations are counted from the starting point of timing. I take it again. The number of oscillations are counted from the starting point of timing. Okay, so where you are starting from is where the timing should start from. So you need to take note of the starting point. What do I mean? Let me show you a typical example using the diagram. Now, from the diagram of the simple pendulum, if I'm starting from point C, definitely I'm starting my timing from point C. That is what I'm simply saying. So if you are taking point C as a starting point, that means you are starting your timing from that point C. If you are taking point A as your starting point, definitely you are starting your timing from point A. If you are taking point B as your starting point, definitely you must be starting your timing from that point B. So that is the first key point you need to know. Now the second key point is that a complete oscillation is made when four phases are covered. Four phases are covered in respect to the reference point. In respect to the reference point. What do I mean by that? What I mean is, for me to have one complete oscillation, four phases must have been covered. Four phases must have been covered. Each phase is 90 degrees. Okay, each phase is 90 degrees, and so that means four phases will be 360 degrees. So definitely 360 degrees is making a complete oscillation, which is making a whole lot of sense from here. Okay, so how do we do the count? How do we know that I'll be able to complete a four phase? I mean, the oscillation has been able to complete a four phase. Now it's very simple. If you are taking point C as your starting point, okay, then it goes to point A, then throw back to point C. Now how do we do the counting of the phases? Now from point C to point B is a phase. From point B to point A, from point B to point A is another phase. From point A to point B again is another phase. Then from point B to point C is another phase, making four phases. So I'm having C to B 90 degree, B to A 90 degree, making 180. Then A to B, that is another 90 degree, making 270. Then from B to C, another 90 degree, making 360 degree. That's why we call it one complete oscillation. So in other words, if you are doing this, you can only count a complete oscillation after the pendulum bulb has gone away from that position and returned back to that same position. Then it becomes a complete oscillation. The same thing applicable to this. Okay, if I pull this down and I release, okay, it goes from here to here, then back to here. So from here to the equilibrium position is 90. From the equilibrium position to this point at the top is another 90, making 180. Then back to the equilibrium position is another 90, 270. Then from the equilibrium position back to its initial position is another 90, making 360 degree. Okay, let's go on. Now I've said it already, each phase is 90 degree, which is also equivalent to pi over 2. Pi is actually 180 degree, so 180 divided by 2 will give you 90 degree. Another way to say that is 1 over 4 of the period. You know, a period stands for the time taken for one complete oscillation. So if I'm dividing a period by 4, definitely I'll be getting the time for completing one phase, which is 90 degree. Okay, so I can as well say t over 4, okay, or I say pi over 2. Okay, so we're in good form with that. So definitely, if you do the arithmetic very well, if this t over 4 from C to B, and from B to A is another t over 4, from A to B again is another t over 4, then from B to C is another t over 4. If you add up the whole t over 4, which is like 4 times, okay, in 4 places, you will end up getting t, which is the period for one complete oscillation. Okay, let's see another one. Now you need to take note of signs in respect to the direction of displacement from the equilibrium position. I take that again. Take note of signs in respect to the direction of displacement from the equilibrium point or position. This will enable you to understand when the variable is maximum. Okay, this will enable you to understand when the variable is maximum. So when you are looking at the direction, you need to take note of the sign. It's very, very important, the sign in respect to the direction of the displacement from the equilibrium position. So if you are considering this as your starting point, obviously the sign of the maximum displacement is positive because it's towards the right of the graph. Okay, and if you are taking this as your equilibrium position, okay, then you need to know that it is negative because it's going to be towards the left. This is towards the left. So when you are considering the direction of displacement, you need to carefully take note of the sign, okay, of each direction, and this will enable you to understand when a variable is actually maximum or not. Okay, let's see other things you need to know. Now, to avoid confusion or the use of wrong sign, because this is where students do have issues. Okay, to avoid the use of wrong sign, I would advise you draw a table to show the variable. Okay, and the variable is your time, your displacement, the velocity, and acceleration. So in your table you can show all these variable and also their corresponding position. So it's better off to use a table. Okay, just make a table, put all the necessary data per each variable. Okay, so this will enable you to avoid a lot of confusion. I'm going to illustrate this later on how to use table to figure out to figure out how to plot the graph. Okay, let's see another one. Another one is you use the variable on the table to plot your graph. Use the variable which you have on the table to plot your graph. Now I need you to know that the displacement to time graph will give you the solution of the equation for S.H.M. It's as simple as that. The solution to the displacement time graph you've plotted from the table will always give you the solution to the equation for simple harmonic motion. Okay, another one, deduce what kind of graph is formed. This is very, very important. Deduce what kind of graph is formed. Cosine graph starts from non-zero origin, while sine graph starts from zero origin. Okay, for cosine graph, the graph will start from non-zero. Okay, meaning that it's going to have a value. Okay, why the sine graph will start from zero origin. So when you have such kind of graph, it's a sine graph if it's starting from a zero origin. Okay, let's see how we can apply what we've learned in plotting a graph in finding solution to equation for simple harmonic motion. Now what I want to do is I'm taking point C as my starting point. So if C is the point the timing begin, that is the point of my displacement, my starting point, then the relationship between the time, displacement, velocity and acceleration is shown in the table below. Okay, so you can see my own table now. This is the table I was referring to that you can use. Okay, so in my table I have all the variables represented. I have the position, I have the time, I have the displacement, I have the velocity, I have the acceleration. And for the position, I'm taking C as my starting point. Okay, so that means I'm having C to C, which is back. Okay, so I'm having C to B to A to B, the back to C. That's why I say C to C. Okay, so this gives me a complete oscillation. I'm starting from here, it goes here, it returns back here. Now let's see how to analyze using the table. At point C, okay, the time is 0 because at that point C, that is the point of displacement, and that is where I'm starting the timing from. So my timing at point C is 0. Okay, now by the time the object moves from C to B, okay, it covers a phase, and I told you for a phase I have T over 4. Okay, so that means here I'll be having T over 4, which is a period over 4. Okay, please, not small letter t over 4, capital letter T over 4, because capital letter T is your period. Now by the time it moves from B to A, I have another T over 4. So definitely from C to A now, I'm having T over 4 plus T over 4, which will give me T over 2. So C to A is T over 2 because it has covered two phases. Okay, now from A to B again, back to B, is another T over 4. So by calculating from C to B, B to A to B, so I'm having 3T over 4 in total. Okay, then from B back to C, I'm having another T over 4. So definitely in all, I have T by adding T over 4 plus T over 4 plus T over 4 plus T over 4. That gives me T. Okay, so that's for the timing. Now for the displacement, at C, my maximum displacement is positive. My maximum displacement is positive. That's why it is positive here. So I put it X maximum because I'm having maximum displacement at that point. Now by the time it moves from C to B, okay, my displacement at B is 0. Okay, because that is a rest position or the equilibrium position. So it's 0. That's why I'm having a 0 at point B. Okay, so from point B to A now, I am having a maximum displacement here, but in this case now my maximum displacement is negative. Why? Because the object is moving in the left direction. It's moving towards the left, so that's why it's negative. So in this case I have a negative maximum displacement. Now the object returns back to B again, and at B maximum displacement is 0. Displacement is 0, so in this case I have 0. Okay, then to C, displacement is maximum again, but positive. Why? Because it's returning in the right direction, so my displacement is going to be positive. So that's to displacement. For velocity now, velocity at point C is 0 because that is the point I'm just releasing the object. Okay, so the object is starting off from C at rest. Okay, so velocity is 0 at point C. Okay, now by the time it moves to B, of course it's going to pass through B to A. So at B it will have the highest velocity. Okay, but at that point B, it is negative. Why? Because the object is moving towards the left of the graph. So it's moving towards the left. So that's why in the table I cited it as a negative maximum velocity, okay, because it's moving in the left direction. Okay, now on getting to A, the object comes to rest again before moving back, so that's why velocity is 0 again at point A. So that's why I have it to be 0. Now on getting back to B, of course it's passing through this place, so it's not coming to rest, so I'm having maximum velocity. But in this case now it becomes positive. Why? Because it's moving in the right direction. Okay, so that's why it is positive. Then back to C now, which is another limiting point. It gets back to its rest position, to its limiting point again at C, and at that point I'm having the maximum the maximum velocity is 0. That is, velocity at this point C is 0, so that's why I have it to be 0. Now let's go to acceleration. At point C, acceleration is negative. Why? Because on releasing the object at point C, the object moves in the left direction, which is negative. And I've told you there is a change in velocity. That's why we said an object accelerates. So when it moves from this point C in this direction, it's accelerating. So that's why we say it has the maximum acceleration at that very point. Now on getting to B, okay, it's going to slow down in a way before accelerating, because it needs to accelerate to reach this limiting point at A. So that's why acceleration at point B is 0. Now on getting to A again, it's going to be maximum. It's going to be maximum. Why is it maximum? Because there's a change in velocity from B to A. But in this case, the acceleration is positive. Why? Because it's going to be returning back to B. Don't be confused. When the object gets here, it accelerates back to B. So there's a change in velocity. But when it's moving from B to A, the acceleration is actually 0, because its acceleration here is very negligible, okay, compared to when it's coming from A to B. This is like descending, this is like trying to ascend, so it's very negligible. Now at this very point it gets here, that is gonna be B. That's maximum acceleration, which is a negative, okay, which is positive rather, because it's moving in the right direction. Then from B to C again, I'm having a 0, because at this point acceleration is 0. Then back to C, at C acceleration is maximum, because it's going to be there's a change in velocity, and so the acceleration is negative at point C again. Why? Because it's going to be moving back again in the left direction. So that's for if we are considering C as our equilibrium position. Now what I've done here is also applicable if we are using a vibrating spring attached to a mass. Now how will the graph look like? Now let's start firstly with displacement to time graph. For displacement to time graph, I'll be using the displacement column to that of the time column. The displacement column to that of the time column. So I'll only be using these two columns. Now in the vertical direction, I have the displacement, and in the negative direction, I have the time. The vertical direction, I have the displacement. In the negative direction, I have the time. Okay, so let's start with the first one there. When the displacement is maximum, which is x maximum here, the time is what? Is 0. So I have a 0 here. So that's why I have this, my plotting point right here. Then when the displacement is 0, the time is t over 4, which is this. So I have another plotting point here. Now when the displacement is negative, which is towards the down of the graph, the downward direction of the graph in this place, then I have the time to be t over 4, t over 2 rather. Then when the displacement is the displacement is 0, when the displacement is 0, is back to 0 again, the time is 3t over 4 in this place. Now when the displacement is maximum, again positively maximum, then the time is t, okay, which is a period. So if I connect all the 4 points I have plotted, I'll be having this kind of curve. Now I've said it earlier on that when the curve, or when the graph starts from non-zero, because the graph is starting from non-zero here, it's not starting from zero origin. So when the graph is starting from non-zero, I told you that such a graph is called a cosine graph. Okay, so this is a cosine graph. Okay, and for every cosine graph there is a formula for it. We have y. So for cosine graph, we have a general equation for that mathematically, which is y equals y maximum cos theta, where the theta there is actually the angle. Okay, the y there is simply the vertical axis. Y maximum is simply the highest point on the vertical axis, which is also the maximum point on the vertical axis. Okay, y, I've explained that over theta being the angle. Okay, now if I relate that to this graph I have right here, I can simply conclude that my y is actually my x, since I'm using x to represent my y here, which happens to be my displacement, and my y maximum is going to be my x maximum, which is what I'm having here. Then my my theta, which is the angle, is simply omega t, which I've said earlier on that theta is the angular displacement, which is the same thing as omega t. So at the end of the day, I'm going to have this equation, which is the solution to the equation for S.H.M according to what I've said before now, that the solution to the equation for S.H.M is actually the equation obtained from the displacement time graph. So basically, displacement time graph gives us the solution to the equation. Now we can as well plot the velocity time graph, okay, for the when the object is still at sea. Okay, so all what I would need to do is to consider the column for time and for velocity. Okay, so those are the two major ones I'll be considering to plot the graph of velocity against time. Now velocity is going to be on the vertical axis and time is going to be on the horizontal axis. Now when the time is 0, when the time is 0, according to the table, what we have on the table, my velocity is 0, so definitely I have the plotting point right there. Then the next one, when the time is t over 4, okay, period over 4, okay, the velocity is maximum but negative, so in that case it will be downward, okay, which is going to be this point. So at this point I have the velocity to be negatively maximum and the time is period over 4. Now the next one, when the velocity is 0, which is this point, the time is period over 2. And the next one, when the velocity is maximum, right here, okay, which is right here, positively maximum, the time is 3 period over 4, which is thrice of period over 4. Then lastly, when the velocity is 0, the period is t, okay, and the velocity is t. So if I join all the plotting point, which is 1, 2, 3, 4 and 5, so if I join all the plotting point together, I will end up getting a kind of a zigzag curve like this, okay, a kind of a wave like curve in this manner. Now if you look at this graph, you will notice that this is a sine graph, and the sine graph is not the same as cosine graph. Why did I say it's a sine graph? Because the graph is starting from the origin, which is a 0 point, and I've said that earlier on, that when the graph is starting from a 0, of course it's going to be a sine graph. So generally for all sine graph, we have an equation for that, okay, which is just like that of a cosine graph, and the equation is simply same as y equals y maximum sine theta this time around, not cos theta now, but sine theta. So if I substitute all the necessary parameter by comparing it with this graph, my y vertical here is actually v, so I will substitute, which is v equals, then my y is actually v, then my y maximum is negative v maximum. So I'm going to substitute, then the next one, theta, is always omega t, so I substitute. So at the end of the day, I'm going to get this solution for velocity time graph. Now from here, remember, v maximum is the same thing as omega x maximum, okay, just like that of circular motion. You know, in circular motion, v is actually equal to omega r, or you can say r omega. So that means my r is more or less same as my displacement, though in circular motion r represents radius, okay, but in this case r is representing my maximum displacement. So if I should substitute for v maximum here, I will end up getting x maximum omega. So this is another way of writing the equation. Now let's consider acceleration to time graph. For acceleration to time graph, I'll be considering the acceleration column and the time column. Okay, so when the acceleration is maximum but negatively maximum, the time is 0. So definitely I'll be starting from the negative axis of my acceleration here. Okay, and the time is 0 when it is maximum negatively here. Now when the acceleration is 0, which is this point, the time is a period over 4. And the next one, when acceleration is maximum, which is what I have here, the time is a period over 2. Then the next one, when acceleration is back to 0 again, the time is 3 period over 4. And lastly, when acceleration is negatively maximum, which is the starting point, okay, the period remains t. So I have a period here. So if I connect, I'm going to have this kind of curve. Now from what I have here, I have the graph starting from the negative axis. So obviously the equation to this graph is going to be a cosine graph equation, which is y equals y maximum cos theta. So but if I replace it with the necessary parameters I have here, variables I have here, which I have used to represent y, I can as well say that my y is my a, which is this, and my y maximum is negative a maximum, which is what I have here, okay, negative a maximum, which is acceleration maximum, then cos omega t. But let's take note that acceleration maximum, which is a maximum, is actually omega square
maximum. Or probably you can as well say that A maximum is same thing as x mass omega square. So if you substitute, you are going to get this value. So it's very simple to compute this kind of equation. So for acceleration time graph, this is the solution. For velocity time graph, this is the solution. While for displacement time graph, this is the solution. But meanwhile, the solution for displacement time graph is the solution to the equation for S.H.M. Now let's see another situation entirely. What if we have the pendulum bob starting from another different position apart from C, maybe from B or rather from A? So what kind of graph are we going to have? Now I need to say this, that we are not going to have the same kind of graph as we are having here. We are going to have different kind of graph entirely. But one thing is that we are still going to be following the same principle. Okay, so let's see a situation. Let's say we have the pendulum bob starting from let's say we have the pendulum bob starting from probably B. Let's take B for example. If the pendulum bob is starting from B, how will the graph look like? Okay, so here we go. Let's see what we are going to have right from here. So yeah, this is what we have. If it is B, which is the equilibrium position, we are starting the timing there. Okay, the relationship between the time displacement velocity and acceleration can be shown as we have in the table below. Okay, so in this case, just following the same principle we used for the initial one when it was at C, okay, we can also formulate the table. So when we are considering B as our starting point, definitely we are taking B as when the time is 0, okay, because we are starting our timing from here. So time is 0 here. So obviously my displacement is 0 because at equilibrium position displacement is always 0. Okay, now when the object is displaced to C, if the object, if this is the starting point and the object is moving in the direction of C, is going in the direction of C, then definitely I see I already know that displacement is maximum. Okay, but this time around the time is going to be period over 4. Why? Because it's covering just a phase from B to C. That is just a phase. So that is period over 4, which is what I have here, period over 4 when it is maximum. That is when it goes to C. Now when it comes back to B, that is another phase, which is 2 phases. Okay, and that will give us period over 2, but in this case displacement still remains as 0. Then when it goes to B, then I have 3 period over 4, which is a negative displacement, maximum displacement. Okay, and when it comes back to B from A, it becomes period, which is 0. Displacement becomes 0 again at B. So obviously 4 phases have been completed. Let me take it again. From B to C, that's a phase. From C to B, that is another phase, which is 2 phases. Then from B to A, that is the 3rd phase. And from A to B, that is the 4th phase, which is a complete cycle. Okay, let's see that velocity. For velocity, we can have V maximum. Already we know that velocity is always maximum at the equilibrium position. Then when it goes to C, velocity becomes 0 because that is a limiting point. That is a limiting point. Okay, then when it comes back to B from C, okay, it comes back to maximum again. But in this case, the velocity is negatively maximum. Why? Because it's moving from C towards the left hand side, which is the negative direction of the graph. Then from B to A, is another is 0, meaning that velocity is 0. Why? Because the object is coming to a rest at A before moving again back to B, where we have the velocity to be positively maximum again. So velocity becomes positively maximum. So the same thing goes to acceleration. Acceleration is always 0 at the equilibrium position. When it goes to C, it is maximum. Okay, acceleration is negatively maximum. Don't forget, at C, at this side, is negatively maximum because it's going to tend towards the side. And when it comes back to B, it is 0 again. Then when it comes to A, it is positively maximum. Why? Because acceleration, the object tends to move in the right direction, so it's moving in the positive direction. And when it comes back to B again, acceleration is 0. Okay, so the same thing is applicable to using a vibrating spring attached to a mass. Okay, so let's see how the graph is going to look like. Let's start with displacement time graph. Displacement on the vertical axis and time on the horizontal axis. Okay, so let's use the table now to plot the graph. Okay, so when the time is 0, displacement is 0. Obviously, that is what I have here. Then the next point, when the time is t over 4, the displacement is positively maximum. That's why the graph is tending towards the positive at this point. So the time is t over 4. Now, when displacement is 0, the time is t over 2. That means the graph is coming back to 0 at displacement is 0, and at that point the time is period over 2. Now, when the displacement is negatively maximum, definitely the graph is going to tend to the negative axis. So this way I have the negative maximum, and the time is 3 period over 4. Now, the last one, when the displacement is 0, the time is period. Okay, is t. So if I connect it, I have a wave-like graph, and because the 0 is starting, the graph is starting from a 0. So this is a sine graph. This is a sine graph, and you can recall the equation I gave to you, that for every sine graph we have a general equation which is y equals y maximum sine theta. So if I begin to substitute for my y, which is my y axis, the vertical axis, so my y is going to be x, because I'm using x to represent my y here, and y maximum is going to be x maximum, then the theta is going to be omega t. Okay, and why is it that y maximum is a positive x maximum? The reason is because the graph is tending first to the positive axis and not to the negative axis. So because of that, my maximum displacement is positive and not negative. So please take note of that. Then for velocity time graph, I have just use the table again, velocity against time. Then you are going to have this kind of graph. Now this is a cosine graph, and for this cosine graph, I have my y maximum to be positive, positive v maximum. So if I substitute, my y is v, my y maximum is positive v maximum, and this is a cosine graph, so I have omega t as my as my theta. Okay, so in this case I'm going to have this equation as the solution for the velocity time graph. Now for acceleration time graph, I'm going to be using the column for acceleration, the data here, and the data for the time. Okay, so if I plot the graph, that is a against t, I'll be having this kind of graph. If you do the right thing, if you do the needful, this is what you will end up getting. Now this is a sine graph. Why? Because the graph is starting from origin, and the y maximum in this case is going to be negative a maximum. Why? Because the graph is tending at first to the negative axis, and so that is why it's going to be a negative A maximum. And I've already explained earlier on that A maximum is also the same as omega square x maximum. Okay, so in this case I will end up getting something like, don't forget the negative, so this is going to be negative x maximum omega square, or omega square x maximum, and the theta remains omega t. Now I want us to relate something together. You will notice that from the defining equation of S.H.M, which is A equals omega minus omega square x maximum, you will discover that as A is increasing, what happens to x maximum? X maximum is actually decreasing. But one thing is that they are decreasing proportionally. Oh, what do I mean? Please don't be confused. What I simply mean is, as A is increasing, acceleration is increasing, the x maximum is also increasing, but negatively. So invariably I can say that as A is increasing, x maximum is decreasing proportionally. Okay, so it's the same thing I'm trying to say. Now if I relate that to the graph I'm having here, I can as well say, consider the graph for displacement time graph. As the displacement is increasing, what happens to the acceleration? Acceleration is increasing negatively. It's increasing in the opposite direction. Okay, I think that should be the best word we can use for that. Okay, as the displacement is increasing positively, acceleration here is decreasing negatively. Now as the displacement decreases from here negatively downward, acceleration is increasing positively upward. You can see now that this graph simply explains the defining equation of S.H.M. So this is a beautiful thing that we can use to justify defining equation for S.H.M. Now let's consider relationship between velocity and displacement. Relationship between velocity and displacement. Now I want to see the relationship that exists between the velocity, and we have considered that of displacement time graph, we've considered that of velocity time graph, we've considered acceleration to time graph. Now we want to consider velocity against displacement. Now this is the kind of graph you are going to obtain if you plot velocity against displacement. It's very simple. All I just need you to do is to fall back to any of those table we've computed. Now use the column for velocity and that of displacement to plot the graph. You will obtain this kind of graph exactly. This is the kind of graph you are going to obtain at the end of the day if you do the right thing correctly. Meanwhile, this kind of graph is an Eclipse. Is an Eclipse kind of graph. Okay, so and generally the equation of Eclipse is y square over b square plus x square over a square equals a. So what I just need to do is to begin to relate this formula, this equation, to the graph. My y is simply the y-axis, which is velocity, that is v. So that's why I'm substituting for v, and my x square, my x actually here is the negative, is the x-axis, which is standing for my displacement also x. So that's why I have x here. Then my b in this case is representing omega x maximum. X naught here is simply representing x maximum. So omega x maximum, that's what my b is representing, and is all squared anyway. Then a here is representing my x maximum. A in this case is representing my x maximum, which is squared. So and everything equals to 1. Now if you do the arithmetic here and try to make v the subject of the formula, you end up getting this equation. You will get v equals plus or minus omega all square root x maximum square minus x squared. This is the equation you will end up getting if you make v the subject of the formula from this particular equation. Now let me buttress this graph a little bit further for those who might still be getting it confused, or if perhaps you are getting it confused in a way. Now from this graph I have here, from the graph I have here, if the displacement is positively maximum, what happens to the velocity? Velocity is obviously 0, so definitely I will have my plotting point in this place, because it's at this exact point velocity is 0 and displacement is maximum. Okay, now if the object moves to B, at B displacement is 0, which is this place, and the velocity is maximum, so definitely at displacement is 0, velocity is maximum. So I have my plotting point here. Now if the object moves from B to A, at A displacement is negatively maximum, but the velocity is 0, so I can only have that here on the graph at this point, because at this point velocity is 0 while displacement is negatively maximum. Now if I go ahead again, when it moves from A to B back, at B displacement is 0 but velocity is maximum. Velocity is maximum at this given point, so it's going to be at 0, the velocity is maximum. Don't forget, when we are moving from B, from C to B, on getting to B, the velocity is negatively maximum because it's moving in the negative direction. So do not forget that. Don't forget your sign. So that's why it is at this point. Now when it comes back to B again, velocity is 0 when the displacement is 0. So I'm still going to come back to this. So it's just like I'm starting from here, then down to this place, then to this place, then to this place, then coming back to this place. So it's going to make an eclipse. So I'm going to have an eclipse right there. Okay, from here, let's quickly look at the relationship between velocity and displacement using a mathematical method. What we have done so far is the use of graphical method. Okay, let's see how we can use mathematical method. Now there are two ways to this. I can either use trigonometric ratio or calculus. If I'm using trigonometric ratio, remember an identity ratio like this: sine square theta equals cos square theta equals 1. And remember, theta is actually omega t. So all I just need to do is to substitute for theta. Anywhere I see theta, I'll put omega t. Okay, so if I do that, I will end up getting this equation 6, which is sine square omega t plus cos square omega t, which equals 1. Now remember, when x equals 0 at t equals 0, when x is 0 and t equals 0, definitely I'm considering when the object is at point B from the diagram we've considered in the previous slide, in the previous page. You will notice that the equation we obtained was this equation. The solution for the graph was this: x equals x maximum sine omega t. Then for the velocity, it was this. Now all I just need to do is very simple. All I need to do here is to find a way to substitute for omega, for sine omega t and cos omega t. It's very simple. How do I do that? All I just need to do is to make this sine omega t the subject of the formula. And if I do that, all I will get is x over x over x maximum. If I do that also here, make cos omega t subject of formula, I will end up getting V over X maximum. So if I now substitute for sine omega t and cos omega t in this particular equation, equation 6 right here, I will end up getting this, which is X over X maximum all squared. What I've simply done is I've substituted for sine omega t. Then I will also have plus into V over X maximum omega. Why? Because I've made cos omega t the subject of formula, so it will be V over X maximum omega. So if I substitute right here, it will all be squared. Then all equals to 1. Then what next do I do from here? Don't forget, what I'm looking forward to is the relationship between V and the displacement. So I will make V the subject of the formula. So by making V the subject of formula, I will end up getting this particular equation, which is same equation as to the one we got when we use the graphical method and applying the equation of eclipse. Okay, from here, since x is 0, which is what I have here, since x equals 0, if I substitute in this equation for x, which is this one, okay, I will end up getting V equals omega x maximum, because what I will actually have is V equals omega x max square, then all square root. Now if I find the square root of x max square, it will give me x max. Okay, and don't forget, omega x max is the same thing as V max. Okay, maximum velocity will give me omega x max. So invariably what we are saying is V is also equal to V max. That is only applicable when x equals 0 in this situation. Okay, so this will be cancelled out because it is 0. Now we have simply come to the end of the lesson for today, and this is actually question time. So I need you to go through these various questions for you to able to get yourself well grounded in what you have learned so far in today's lesson. Okay, so I have the first question here, which is state two conditions necessary for a mass to be undergoing simple harmonic motion. Okay, I have stated those conditions when defining simple harmonic motion. So you need those conditions right here, and you get your 2 marks. Okay, actually these questions are extracted from Cambridge past questions, so you can as well search for them or try to look out for them in the various years. This is another question. The first question is calculate the angular frequency omega of the oscillation. This is a continuation of this particular question here. Okay, so you need to go through this question. You can pause the video, pause this video, and look at the question critically, okay, before answering them. So this is a continuation of the question. This is another question entirely. Okay, this is a continuation of particular question here. Okay, then this is a continuation of the question again. Then we come to the end of the whole question right here. Now in our next lesson, we shall be considering restoring force. We want to see how forces can act on the oscillating body. Okay, and what does restoring force actually mean, and what is even the function of restoring force? So in our next class we shall be considering this. So on this note, I'll be looking forward to see you in the next lesson.